Students, this is a fantastic equilibrium question. It gives us four gases that are in an equation, and they give us an initial concentration for all of them of 0.9, and they give us a value of K of 3.75. Let's start by writing expressions for K, and for once we're going to actually have to really consider the expression for Q. Since everything is a gas, everything belongs both in the equilibrium expression and in the ice table. So if I were asked to write an expression for K, I'd say, okay, I'll take concentrations of both reactants and raise them to the power of their coefficients. But the coefficients in both cases are 1, so we have implied exponents of 1. And for Q, I'm going to include subscript 0 to indicate initial concentrations. That subscript 0 has no mathematical meaning. It's just there to indicate something other than the equilibrium concentrations. Now in this question they say that the initial concentration of all four gases is 0.9. So let's actually calculate Q for this equation. Most of the time you can get away without having to calculate Q, because in the ice table there's usually an initial concentration of 0. And if you have an initial concentration of 0, then you always can shift to the side with the 0. In this case, Q works out to be 1. And since Q is less than the stated value of K of 3.75, then we know that we will shift right. So that means in the ice table, we're going to put our pluses on the right side and our minuses on the left side. Let's start fleshing out that ice table. They had given us 0.9 for the initial concentration of all gases. And we've just figured out that we'll make the pluses on the right side and our minuses on the left side. The coefficient for every single species in this equation is a 1. If it were something other than 1, we would have to carry through the coefficient in the changed line of the ice table, which would then affect how we calculate equilibrium concentrations. But here we're just filling out our ice table and letting the sum of the initial line and the changed line be equal to the equilibrium line. Now, how do we handle it from here? Well, if we know that the expression for K involves product gases multiplied together and reactant gases multiplied together, then, let's see, oops, well, we'll just write below it here. So 0.9 plus x times 0.9 plus x all over 0.9 minus x times 0.9 minus x equals the value of K, which they gave us at the beginning of the problem, of 3.75. Now you can probably see a perfect square here, and we'll use that to our advantage to make the equation simpler. 0.9 plus x times 0.9 plus x is simply 0.9 plus x squared. And in the denominator it's 0.9 minus x squared. Now we'll take the square root of both sides of this equation. let's see, the algebra is okay, but it's going to get a little tricky. 0.9 plus x all over 0.9 minus x equals 1.936. I'll multiply both sides of the equation by 0.9 minus x. Allowing 0.9 minus x to cross out. The 0.9 plus x still remains. On the right side of the equation, we get 1.74 minus 1.94x. And let's see if we can slide this up a little bit. I'm going to add 1.94x to both sides to get 2.94x on the left side. And then we'll subtract 0.9 from both sides to get 0.84 on the right side. We'll divide both sides by 2.94, and we get x equal to 0.286. So if x is equal to 0.286, and we know from our ICE table that the concentration of SO2 and NO2 are both 0.9 minus x, and the concentration of SO3 and NO2 are 0.9 plus x. Well, then we now have a value of x, and we can make our final calculation. I think I'll just kind of start fresh here. So if I'll rewrite the expression for K. .9. Oh, actually, we do not need to calculate K. They already gave us K. So in this equation, we just need to find out what the value of SO3 and NO2 are, which would be 0.900 plus x, and SO2 and NO2, which would be 0.900 minus x. So that's 0.9 plus 0.286, which works out to be 1.19. And for the SO2 and NO2, .614. And those will be the two gases of each type. The reactant gases and the product gases will be the same.